we'll now talk about the more advanced algorithms after we saw the current vanilla method, faster RCNN, SSD. We can see methods that usually can be added on top of that and improve accuracy. So the first one has a line that promises a lot and even works well. It improves object detection with just changing one line of code. If you look at this example, we have two detections with large overlap. And these are indeed two different objects which are very close together. And both of them got very good scores. But if we use greedy NMS, then we would lose the other one. But this is not something that is wanted. We would pretty much prefer to just reduce the score, the confidence that we have in this example, and not lose it completely. So how is this performed? Basically, if we take a greedy NMS, then decision is discrete. If the overlap is over a specific threshold, we take the score and zero it. Otherwise, we keep it as it is. Now, we can use something similar that would basically take the overlap and use it to factor the new score, if it's above or below threshold. But this creates a problem where, again, the decision has some sort of barrier on a specific IOU criteria. So the way that it's done in this paper is by smoothing the decreasing of the score, basically replacing the score with some sort of function. As you can see in this code, the score is multiplied by a function that takes the IOU as input. So this has pretty much a steady improvement on all algorithms that it's been applied on. So it's pretty much a shame not to use it in your algorithm, and I think that most state-of-the-art algorithms do in the current submissions. You can also see here that the accuracy is pretty much stable across hyperparameters and algorithm, where the NMS basically, the soft NMS basically improves over the accuracy of the greedy NMS. So can we do something even better? The NMS is actually the only part of the algorithm that isn't learned during the training. And it's actually also a part that's different between training and testing. Because as we said, during training, we take all examples that have over 50% intersection of a union. But during testing, if we have multiple detections of the same object, then we would consider the rest of them as falses. So because we don't train the same way that we test, we're maybe losing some accuracy. So this method suggests to train the NMS as well. And the way that they do this is by adding these two contributions. The first one is the additional block that you can see in this image. Each block takes all the detections and basically take the features that were extracted for that region, and it combines them with all the other regions. So we get basically n times n computation, and this gives us a new feature vector that contains not only the info on the object in the image, but also the relation to other objects, their position and the confidence. So this process is repeated a couple of times, and this basically allows the network to learn the relationship between detection. The final addition is a new loss that punishes more than one detection per object. Instead of taking all of the positives as positive, we take only one detection per object, and the rest are falses. So this makes a much harder task to learn, but thanks to the new blocks, we now have the information to make this work. So here are a few examples of how exactly it works. Basically, instead of having windows which have low overlap pass on, just a second, we can apply the learned maximum suppression and remove them. Yes?
Two questions. First, what is the penalty on test time when we use Second, does this loss completely replace the smooth L1 loss that is used in other methods, or are they used combined?
So this is just for the classification, and you still need to fine-tune your detection using an L1 loss. Now, the additional cost is quite large, I think. I don't remember the exact numbers, but you can guess that combining all the information from all the window pairs and adding many more fully connected wouldn't be cheap. I've experimented with it a bit, and you can actually maybe get some simpler solution of that to work. I think that the key is in the loss itself and not the additional blocks. So how well does it work? It works pretty well. Basically, if we'll take the greedy NMS and try it with different thresholds, we'll get a different precision recall curve for each of those settings. Now, each of those settings is preferring different configuration, if it prefers precision or recall better. The learned NMS basically learns the best of all of these options, as you can see here in the plot. Basically, it learns in each specific scenario, it learns which threshold to choose. And you can see the improvement as it's specified here. While it's not that large, you can see that it is larger where there are more occlusions. Okay, so now we'll take a look into multiscale object detection. Basically, the way that we performed multiscale object detection in the classical days was to take the same algorithm and basically apply it over different sizes of the image. We take the image, we make a pyramid out of it by scaling it, and apply the same model again and again. This is similar to what we saw that was applied in overfit. But this is, of course, very slow because it means we have to apply the same model again and again. So what's the solution? Like in RPN, we can just use a single scale. We take the image, extract the features, and predict using those features all of the objects and all of the sizes. But this is also problematic because those features are not necessarily good for all kind of objects. So we already know that SSD solves this problem, and we can basically, instead of using just one layer of features, we can use multiple layer of features and use prediction from all of them. But the problem with that approach is that the lower level features have much less processing done to them than the higher level ones. So we expect them to perform less well than the other ones. And if you think about this, it's pretty problematic because small objects which use this feature layer are more difficult. So you would expect to apply more feature extraction at that point to make stronger classification. So the solution to this problem is called feature pyramid network by the guys from FAIR and Facebook. Basically, they take the same idea as SSD and recombine the features in a way that makes all the features be with the same strength. So finally, we get a new pyramid with stronger features, and we apply prediction from each of those levels. So how do we combine the features from one level to the next? Basically, we upscale the features from the upper level, and we sum it with the features from the lower level after a convolution is applied. So again, how well does it work? We can see that when FPN is compared to RPN, we get much higher level of accuracy. And this is firstly thanks to the number of anchors that are applied. When RPN scans the image, it only scans 12,000 windows. But when FPN is applied, because of the low stride, it scans many more windows. So how beneficial is each part of the algorithm? Basically, we can compare the top-down pyramid, just the bottom-up, or don't do the literal, or only take the finest level, and we can see that each of those steps are very important and improve accuracy a lot. When we compare the FPN to the feature extracted in FastRCNN, so that means if we use FastRCNN over the FPN features instead of just the RPN features, we can see the same thing, where the accuracy of the FastRCNN improves. An interesting thing here that we can, instead of using the feature pyramid, we can use just the low-level features, only the finest level, and get pretty much the same level of accuracy. So this method is called focal loss, and it basically uses the feature pyramid network and build on top of it with their new loss. So you can see here the model. Basically, we use the feature pyramid network to extract the features. And from each level of features, we apply the subnet for classification and localization. And in this example, they used pretty heavy heads to do that. This is why they get very good accuracy. The goal of this work was actually to check how well can a single-stage detector work when compared to two-stage detectors. Because at that time, it was believed that first-order CNN is more accurate than SSD, for example, because it has two stages. So, as I said, the second contribution is the loss itself. And as we discussed earlier, a problem of object detection is the unbalance. And the way to solve it is hard negative mining, usually at 1:3 ratio. But when we do hard negative mining, we error the model basically by only looking at some of the samples in the image at every step. This means that at each step of the optimization, different proposals are chosen to be the hardest, and this is why only they affect the learning. So we would like instead basically to look at all the proposals all the time, and this will help us get more stable learning. So the way that they did this is first to have some sort of baseline, which is weighted cross entropy. Instead of just taking the cross entropy, they weighted the loss of each class by some sort of predefined weight. And in order to build over that, they basically added the focal loss. Now, if you remember in hard negative mining, we wanted to give harder example more weight by only including them. So in this loss, we factor the weight of the loss according to how wrong or correct it is by adding the factor that you can see here. And you can use a constant basically to control how much to punish the hard and easy task. And we'll see later on how it works. So they tried different parameters, and in order to find the best one, including the number of anchors or the parameters for the focal loss. But the most important comparison is, of course, with hard negative mining. You can see in hard negative mining that the training is not very stable. If I take different batch sizes or different NMS threshold, I get very different accuracy. This is because of the fact that I've mentioned earlier that not all samples are taking part in every batch. Instead, focal loss does not suffer from these kind of problems because we don't have a batch size, and all samples are being used at every batch. So again, here is a good example on how you can take your network and get some different speed accuracy trade-offs. You can take different network. You can take ResNet 50 or ResNet 1001 in this example. You can take different scales, and you get different level of accuracy. Of course, deeper the network, the larger the input, the more accurate it is, but it's also slower. So in terms of the benchmark results, they show that they have accuracy which is equal or superseding to the methods that they compare to here, even if it's single stage or two stage. This is currently not considered to be a very good result. The current state of the art, which are usually two stage, are around 50 average precision. So while this is an interesting comparison, it's not very updated. So another recent improvement that I recommend you read is the Deformable Convolution Network. If you've been in our previous meetup, then Yossi talked about it and you already know it, so you don't need to read it. But for those of you who weren't here, I suggest you read it. So some more videos that I recommend you see if you want to get deeper into object detection. First, the great lecture from CS231 and the CVPRA 2017 workshop by Kaiming He and Ross Girschik. So thank you very much for coming. I hope you enjoyed it. If you liked what you saw here and you want to come work with us, feel free to send us an email or talk to us. Thank you.